Hello friends and welcome back. So in this session I am going to cover one of the important topic of Kubernetes architecture, which is called the ETCD quorum. Okay, so ETCD is one of the important and critical component of control plane in the Kubernetes. Okay, and for high availability of ETCD it follows the quorum, which is called the majority rules. Okay, but it is a bit confusing and I have seen many confused engineers specifically in this topic, what is quorum, and then when you ask like how it works, how we calculate the quorum, and how many control planes we need. So they would not able to answer that, okay, because they do not have a clarity on what exactly is the quorum and how it works. Okay, so in this session I am going to explain in a very simple way so that you will understand what exactly is the meaning of quorum. Okay, so the very first thing, etcd quorum means the majority rules, and if you see the definition, okay, so what you will see at multiple places, etcd use the raft consensus algorithm. A right is only committed once a majority of member acknowledge it. What does it mean? The right is happening only when a majority of member acknowledge it. The majority is called the quorum. The very first thing is, what is the meaning of quorum here? It is the majority. Okay, and the majority of etcd component. Right. So I will explain you in three different sections, referring three different sections. The one is the high availability architecture. Second is the type of request, and then third will come on the quorum majority. What is the meaning of that one? Okay, so now here let me draw an architecture. So whenever we build the Kubernetes, okay, cluster, okay, so we have the multiple control plane nodes and multiple worker nodes. Okay, so basically how we decide how many control plane we need and how many worker nodes we need. Okay, so now for that, to understand that, we need to understand the request type. Okay, so we have a two kind of a request. The request one, which is coming from the control plane. Second request, which is for the applications. Right. So that means the end users are interested in your applications only, which you have deployed in the worker nodes. Right. And control plane is specifically for the Kubernetes cluster component, and which is managed by the administrators who is managing the Kubernetes cluster. So that means when we design the high availability architecture, you have to consider two things in mind: the number of worker nodes where your application going to run, and the number of control plane node. So if control plane is not node is not working, then your application will also get impacted. Okay, so we have to ensure the high availability at both end, control plane as well as the application end. Right. So now how we decide like how many control planes we needed. Okay, so I will draw a simple architecture, basic architecture, the or you can say the minimum architecture that we follow in the production. Okay, so the minimum architecture in production is we have three control plane nodes, one, two, three, and below that we can have any number of worker node based on the load in our application. Okay, so suppose that we have four worker nodes. This is worker node 1, worker node 2, worker node 3, and worker node 4. And this is our control plane 1, control plane 2, and control plane 3. Right. So our applications are running here in this particular worker nodes, right? So basically what will happen in this situation, the users going to access your applications, okay, from the worker nodes. You have deployed the application here, okay, and you may have some users, okay, they will connect to your worker nodes where the applications are running, like this one. Okay, and here in between you may have the load balancer, okay, for load balancing the request, and where we have the node port service in the Kubernetes, and that is specifically to get the access of the application which is deployed in the worker node. Right, this is the very first thing. So now apart from that, you have the administrators as well, right? You have the developers, you have the administrators, right? Who is doing the management of the resources, which is there in your complete Kubernetes cluster. Right. So this is the first traffic and this is the second traffic. So now what we are talking about, we are talking about the high availability of this control plane node. Okay, not the users. So here the minimum architecture, what I said, the minimum number of control plane node that we design in the production environment basically. So number at least three at least. Okay. So now you know that in the control plane we have four important components, right? The first is the API server, which is the backbone. Okay, and then we have a ETCD, then we have scheduler, and then we have control manager. Okay, so all these four components are here as well in each and every node. Okay, now when we any request comes like from the developer or from the administrator, okay, so it can be diverted to any of the API server. So we have 1, 2 and 3 API server, right? Similarly, we have 1, 2 and 3 ETCD, 1, 2 and 3 scheduler, 1, 2 and 3 control manager on the each and every separate node. Now what is happening whenever the request any developer or administrator runs some command like kubectl get pods, it will land up on any of the node, any of the control plane node. So first it reach to the API server, which is the backbone. Every communication is happen with the help of this API server. So your API server first get the request, okay, and then from it API server, okay, it reach to ETCD data, which is the main database of resources, right? All the resources like the number of pod or whatever the resources that you have in your cluster, it is maintained in your ETCD, right? So this is going to contact the ETCD to get the complete details. Okay, so now we have two kind of operations, read and write. So maybe the developer, okay, who is trying to access a cluster, maybe the developer is running the command kubectl get pods. So this is just a read command because it is trying to get the pod, whatever the number of pod that you have in your system. Okay, this is called the read request. Second is called the write. So maybe developer is trying to do some modifications in your resources. For example, he is applying or she is applying some deployments. He is doing some deployment. Maybe the developer or the administrator deleting some pods, or maybe it is doing some scaling of your environment. So all these things are going to create or delete the resources in your environment. So this is called the write operations. So even it is a read operation or it is a write operation, everything will be happen with the help of ETCD. If it is a read operation, your API server is going to read the resources from ETCD. If it is a write operation, your API server is going to write to the ETCD. Right, this is a very basic thing. But the catch is here. As I said, we have a 3 control plane node here, and the request can reach to any of the API server, right? After that, as I said, request reach to ETCD, but just like the API server, as I said, API server, all 3 API server will be active at a time. All 3 are active, but ETCD, okay, is not, you can say, active all the time. Okay, the first ETCD will be in the read plus write mode, which is called the leader, and the rest two ETCD are the followers, which is mentioned here. Okay, so ETCD, one is the leader, other are the followers. So if we have 3 control planes, 1, 2 and 3, so only one will be there, which is the leader who is taking the decision to read and write. Okay, and others are the followers. That means they are taking the decisions from the master ETCD or the leader, which is the leader. Suppose this is the leader, this is the leader. So rest two ETCD here and here are the followers. So they are taking the instruction from this ETCD. So that means ETCD, only one is the leader, other are the followers, right? So this is the main difference between your API server and ETCD. In API server, all the API server will be active at a time, but ETCD will be active only one, which is the leader, other are the followers, which is taking the instructions from the ETCD. Okay, that means if the request reach to any of the API server, like here, first, second, third, anywhere, it will first land up on the API server, right? From API server, doesn't matter if it is landing on node 1, node 2 or node 3. The request will always come to the leader. Suppose this is the leader on the host 1, node 1. So request will always come to ETCD. Then ETCD will decide if it is a read operation, okay, then it can be read from node 2 or node 3 as well, because this is just a read operation. If it is a write operation, then ETCD will write on the primary node or on the node wherever we have the leader ETCD. Okay, and once the write is done here, okay, then it is going to replicate to the other ETCD nodes at the same time. Okay, that means read can be done on any node, but ETCD decide which follower can give the read information, or itself it can give the read information. But if it is a write operation, then the primary ETCD, which is the leader, this leader is going to write, okay, but other followers is going to take it when the ETCD write itself in the database, and then it send the information to the other other ETCD. Okay, now here is come the questions or the concept of quorum majority. How the failover or the majority work in case of ETCD. Okay, now let me explain you in a simple way so that you will understand what is the quorum. Okay, so far I have explained the basic architecture so that you can have understanding how API server works and then how ETCD works. Okay, so API server all the active at a time. ETCD only one is the leader, other are the followers. ETCD decide like from where to read. Okay, and also if it is a write, then it is writing on the primary ETCD and then it send it to the followers. Okay, now what is the meaning of quorum here? So let me explain you in a simple way. So here, if you see this document, okay. So let me delete this one. So this is clear, right? ETCD plus followers. This is the architecture of your ETCD. Okay. So now, important thing. Whenever we decide the architecture of our control plane, or you can say Kubernetes cluster, we always go with the odd number of control planes. 3, 5, 7, 9, and it is starting from 3, right? 3, 5, 7, 9, 11, something like that. And that's why I said 3 is the base in the sense the minimum high availability architecture that we design in the production. Okay, if 3, that means we are going with 3 control plane. If 3 control plane, we have 3 API servers, just I explained. Similarly, we have 3 ETCD, and then similar we have 3 schedulers and 3 control managers, right? But why odd? The question is why odd? Why we are going with only odd number of control planes? Why we are not going with 4, 6, 8, 10? Why we are not going with the even numbers of the control plane? Why we are going with the odd only? And this is where the concept of quorum is come. Okay, now simple. The very first thing, quorum, what I said, quorum I said means the majority. Okay, so when the majority is available or the majority of number of ETCDs are available, then only your Kubernetes cluster is going to work. Now what does it mean? So here you can see number of nodes 1, 2, 3, 4, 5, 6, 7. Quorum needed 1, 2, 2, 3, 3, 4, 4. Fault tolerance 0, 0, 0, 1, 1, 2, 2, 3. What does it mean? The very first thing, the formula to decide the quorum is n divided by 2. This is 2 plus 1. Okay, this is called the quorum, means majority. Okay, that means for a cluster or for a Kubernetes cluster to working perfectly, to be up and running, you need this majority of the number of servers, control plane in your cluster. N by 2 plus 1. N is the number of nodes. N is the number of nodes. So now suppose that if I say the number of node 1, 1. So what is the calculation? 1 by 2 plus 1. So if I decide 1 by 2, this will come 0.5 plus 1. So whenever we have this kind of a calculation which is in zero point 0.5, so we round up to the lower end, not to the upper end. So if I round up 0.5 to the lower end, it is 0. 0 plus 1 equal to 1. So that means if we have a one node only, one control plane, so this control plane always need to be up and running. That means majority is 1. Okay, fault tolerance is 0. That means there is no fault tolerance. If this goes down, then everything goes down, right? We have only one server. Now suppose that we have two control planes like this one. So what is the calculation? 2 by 2 plus 1 equal to, this will again come to 2. 2 by 2 is 1, 1 plus 1, 2. So that means the majority is 2. So if we have two nodes in the cluster, two control plane, both always have to be up and running because the fault tolerance is 0, because this calculation is coming as 2. So that means if you have two nodes, both need servers control plane need to be up and running. If out of two any one goes down, the other also will not respond. This is similar to the 1. So that means fault tolerance is 0. So if we have a one control plane, if it is goes down, everything is down. If you have two number of servers, and again if only one of them is down, okay, the complete control plane, complete architecture will be down. So why I need two resources, two control plane? It is just like the one, right? So that means I am wasting one control plane here, right? Now similarly, let's come to 3. So 3 by 2 plus 1 equal to 1.5 plus 1. So 1.5 I will round up to the lower end. So that means come to 1. So 1 plus 1 equal to 2. So here the majority is 2. Quorum is 2. That means in your architecture, 2 control plane nodes should have been up and running always. So that means now out of 3, 2 should be up and running. So now we have the fault tolerance 1, right? So that means if we have 3 control plane nodes, if one goes down, out of 3, 2 will be available up and running. And that's why this is called the basic minimum architecture. 3 node is the basic architecture where you need at least in the control plane, because we have the 1 fault tolerance. Now come to the 4. So 4 means 4 by 2 plus 1. It is 2 plus 1, 3, right? So that means if you have a 4 control plane nodes, 3 need to be there up and running. So, how many remaining out of 4? 1. So that means fault tolerance is 1. Now again you compare. If we have 3 control plane nodes, we have fault tolerance is 1. We have 4 control plane nodes, again fault tolerance is 1. So that means if you have a 3 control plane, if 1 is available, that is fine. If more than 1 goes down, your cluster will be down. Same is in 4 as well. If you have a 4 node, fault tolerance is again same 1 which is there in 3. So if out of 1, if suppose more than 1 is down, your complete cluster will be down. So what is the meaning of 4? If it is behaving like 3, that means we are wasting 1 extra control plane node. That is not required because the quorum is only same 3, right? So fault on which, what is the major differences here which decide the quorum? Okay, the calculation what I said, n by 2 plus 1 plus the fault tolerance. Like if the fault tolerance is same in 3 node and 4 node, right? So why should I go for 4? They're not required. Similarly, if you go for 5 node and if you go for 6 node, so 5 node you have a fault tolerance 2. That means it can survive 2 failures. If it is a 6 node, again the fault tolerance is 2. It can survive the 2 nodes, 2 failures. So why we go for 4? If the fault tolerance is 2 in the 5 node and same 2 in the 6 node, then why should I go for the 6th? I am wasting 1 control plane node here as well, right? So that means whenever we design this control plane architecture, we go with the n by 2 plus 1 formula for to decide the majority or the quorum, and it gives you the fault tolerances as well. How many? What is the fault tolerance? So we have seen here, whenever we have the even number of control plane, we are wasting 1 or 2 control plane nodes there, right? So this is the reason we always go with the odd number of control plane nodes, and this is how we calculate the majority, or you can say the quorum, and then fault tolerance, and based on that we decide we should go with only with the odd number of control planes. Okay, so what I try to explain you here, let me summarize it. Okay, so very first thing what I explain, high availability architecture, that we have two kind of architecture. One is for the control plane node, second is for the application. Your applications means the user that is accessing your application. Okay, that is a different flow. Now control plane, where your administrator and developers are connecting to your control plane node, right? And then we have a read and write operations. So this is a read operation, and these all are the write operations. Okay, so each read and write operation is handled by the first API server. API send this request to the ETCD. ETCD, only one is the leader, other are the followers, and this leader decide from where to read and how to write. Okay, write is happening at everywhere, but it is decided by the leader, right? And then how we decide the quorum majority is n by 2 plus 1. N is the total number of nodes, n by 2 plus 1. This gives us the quorum, the majority that is required, and then the remaining is the fault tolerance. And based on that, we have calculated the odd numbers are the good for the control plane, because if you go with the even numbers, you are wasting your control plane node. Okay, so hope now it is clear to you how this Kubernetes architecture work, and then what is the meaning of quorum.